Okay, now let's take a look at how we can add and subtract vectors algebraically, which is more accurate and faster if we have the vectors expressed in component form or with magnitudes and angles. This would be more convenient to add them algebraically. So kind of taking a look at the same vectors that we added and subtracted graphically in the last video, let's just look at a different way we can add these same vectors algebraically. So the first thing that we would want to do in order to add them up algebraically is we need to find their components. So we'll express these vectors in component form. So going back to our definitions, remember that this was vector A, and then we had this is vector C, and vector B over here. So these are defined on this grid, but we can extract their components from this. And so vector A moved over 1, 2, 3, and x. So its x component was 3, and the y component, it moved 1, 2, 3, 4, 5, and y. So its y component was 5. So that we can express the vector A as 3, 5 here. Vector B moved to the left, so that'll be a negative 1, 2, 3, 4. So vector B will be negative 4 in x, that's the x component, and the y component will be 1, 2, 3, downwards 3, or negative 3. And lastly, vector C was to the right 2 and down 2. So this will be vector C can be expressed as a positive 2 for the right and a negative 2 to move down. Now, adding the vectors together is really just adding up all of their components. So we can say, we call this the superposition principle, which we can add them up. So the resultant in x, the x component of the resultant vector, which the resultant is the same here, it's a plus b plus c, or it's b plus c plus a, as we saw previously. It is commutative, so we can add in any order we want. The resultant, the x component of the resultant would be the x component of vector A plus the x component of vector B plus the x component of vector C. Also, the y component of vector A would be the y component, the y component of the resultant vector would be the y component of vector A plus the y component of vector B plus the y component of vector C. So basically, if we line these up one on top of the other, we can just add like this. For the x's, add like that for the y's. So the resultant vector is going to be, we have ax is 3 plus bx was negative 4 plus cx, which was 2, and then ay was 5 plus by, which is negative 3, and plus cy, which was negative 2. And then adding these together, we see that the resultant is equal to 3 plus negative 4 plus 2 is 1, and 5 plus negative 3 plus negative 2 is 0. So we see that the resultant, when we add up the components here, we add it algebraically, or adding via the component method, the resultant is 1, 0, meaning that it moves over 1 in x and 0 in y, which is exactly what we found when we did the graphical sum previously. Actually, this was our resultant from the graphical sum. So we end up with the same thing. It's a little more straightforward, and it's definitely cleaner, especially if we don't have our vectors defined nicely to grid points to add them algebraically. Same thing with vector subtraction. If we take a look at the vectors we subtracted previously, we'll just do this vector difference a minus b. Let's do this. So we need to define, actually I guess we'll do both of these. So let's go ahead and define what these vectors are. We have vector A was 1 to the right and 1, 2, 3, 4 upwards. So we'll define vector A as this was 1 right and 4 upwards. Vector A. Vector B was simply 1, 2, 3, 4 to the right, and it didn't move at all in Y. So B, vector B is 4, 0. And vector C moved to the left 2 and down 1. So vector C can be written as to the left 2, so this is -2, down 1, -1. And then we can do any sort of operations we want. We said that vector difference D is, we define this to be A minus B. So let's write this out here then. D, should I use the same color? D equals A minus B. These are all vectors here. So A minus B, this will be AX minus BX in the first one. AX minus BX, and then AY minus BY here. So vector D will be AX was 1 minus BX, which was 4. So 1 minus 4, and AY was 4 and BY was 0. And so this is equal to -3, 4. This was vector D, adding it via component method, or adding it algebraically, which is, if you notice, that's the same thing that we got when we did it with the graphical sum as well. So D was -3, 4. Lastly, we can redo vector E. So vector E over here, we said was B minus C plus A. So vector E is equal to vector B minus vector C plus vector A. So just taking these components, this is going to be, the x component will be bx minus cx plus ax. So bx was 4 minus cx, which is -2, so minus -2 plus ax, which was 1. And then by will be, by was 0 minus cy, which was -1, so minus -1, and ay was 4, so plus 4. So then vector E is equal to 4 minus -2 plus 1 is 7, and 0 minus -1 plus 4 is 5. So vector E was 7, 5, which again was the exact same thing that we found via the graphical method previously. So adding it using the component method or adding it algebraically can be a lot easier, a lot more accurate, as well as less time consuming than adding it graphically. But it's always good to be able to add it graphically to double check your work and kind of get an idea of which quadrant we're in.